Imagine the ancient, uh, the very quiet board game of Go. Sitting there placing stones.
Right, very meditative.
Exactly. But
Okay.
now replace that wooden grid with a high voltage neon circuit.
Oh, yeah. That changes the vibe entirely.
It really does. And swap those static pebbles for active 360-degree lasers.
That's just such a wild concept to wrap your head around.
It is, and that's exactly what we're getting into today. Welcome to today's deep dive. Our mission here is to explore a fascinating open-source GitHub project called GoLuminamics.
Yeah, it's an incredible repository.
It really is.
Uh,
We are going to unpack how this project takes the territorial depth of traditional strategy games
Right.
and it collides it with the continuous real-time physics of light.
Which is, it's not something you see every day in board game design.
Not at all. So if
Yeah.
you're someone who loves a good aha moment where complex systems suddenly click, or, if you've ever felt that moving pieces on a board feels a bit too static, this breakdown is for you.
Because in this game, light literally becomes your path to victory.
Okay, so let's unpack this. We are looking at a game where you don't just occupy space. You're basically building an intricate, glowing optical network to fire lasers at your opponent.
Right, and that transition from a static geographic presence to a kinetic physics system, it completely rewires the concept of territory.
How so? Fundamentally, what changes?
Well, in traditional games, right, a stone or a pawn exerts influence just by existing on a specific square.
Yeah, it just sits there and blocks things.
Exactly. But in GoLuminamics, the pieces you place on the board are conduits. They manipulate an active energy source.
So they aren't just walls.
No, not at all. You aren't just blocking off areas. You are managing a live optical circuit that can change instantaneously based on, just a single adjustment.
That sounds incredibly stressful, but in a fun way.
Yeah.
But before we fire any lasers, we need to understand the battlefield.
Right, the grid itself.
Yeah. The repository documentation notes that the board is highly configurable. You can play a quick, highly aggressive skirmish on a tight 9x9 grid.
Which is pretty chaotic.
I bet. Or, if you want a massive strategic campaign, you can scale it all the way up to a sprawling 39x39 grid.
Which is just, that's massive.
Just for context, if you're picturing this, a standard Go board is 19x19.
Right.
So doubling those dimensions to 39x39 creates an incredibly vast canvas.
It really does. It's a huge amount of space to manage.
On this canvas, you deploy 4 specific types of optical stones. Let's walk through the arsenal here. First, you have prisms.
Right, and prisms just transmit the laser straight through, like a window.
Okay, simple enough. Then you have mirrors.
Which reflect the laser at an angle.
Right. Then there are splitters.
Now, these are interesting. They take a single incoming laser beam and branch it into 2 separate diverging beams.
Which sounds like it could get out of hand quickly.
Yeah.
And finally, blockers.
Yeah, blockers just completely stop the beam dead in its tracks. No reflection, no splitting.
So it's essentially plumbing, but for photons.
That's a great way to put it.
You're laying down pipes, joints, and pressure valves.
Oh,
Except the medium flowing through them is a high-speed laser beam.
exactly. And each of these components alters the geometry of the light in a very distinct, mathematically predictable way.
So no dice rolls?
No, zero randomness. The design maps physical optical properties directly onto strategic control.
Okay, but if we follow that logic, I assume the territory mechanics have to be fundamentally different.
Oh, completely.
Because in a normal game of Go, I'd build a physical wall of stones to claim an empty corner.
Yeah.
Here, the territory must be defined by where the light flows, right? Rather than the pieces themselves.
That's exactly it. The territory is exclusively defined by the light.
So how does that look when you actually play?
Well, when the lasers fire, any empty intersection on the grid that your beam illuminates becomes your claimed territory.
Oh, wow. So you don't need to surround it.
Right. You don't have to painstakingly build a perimeter around 20 empty spaces. You simply need to engineer a path that bounces a laser beam through those intersections.
That is wild. It totally eliminates that arbitrary zoning you see in a lot of modern territory games.
Yeah, it creates a pure skill-based system where spatial reasoning dictates the score.
Okay, but that makes the splitter piece sound incredibly potent.
Oh, it is. It's probably the most powerful piece.
In a static game, a piece usually only controls its immediate neighbors. But placing a single splitter in this system, one beam hits it, and suddenly you have 2 beams shooting off in different directions.
Yep. Illuminating entirely new swaths of the board.
And potentially bouncing off mirrors you placed, 10 turns ago. It's a massive multiplier for your territorial reach.
It really is. A single splitter fundamentally alters the whole board state. Because the geometry can radically change with one well-placed component, players cannot rely on passive, static defenses.
You can't just turtle up.
Exactly. You have to actively manage your expansion.
Yeah.
But to prevent players from just, spamming splitters everywhere.
Right, which would just break the game.
Yeah, the game relies on a strict energy system to pace the match.
Okay, let's talk about the economy. How does the energy work?
So players start the game with 10 energy, and they gain 2 energy per turn.
Okay, managing an economy adds an entirely new layer of friction.
It really does.
But wait, if you gain 2 energy per turn, and the documentation says placing a stone costs 1 energy, you actually have a surplus.
You do. You net 1 energy every turn if you only place 1 piece.
That implies banking turns is a viable tactic, right?
Absolutely.
Like you could theoretically pass a few turns, let your energy reserves build up, and then execute a massive combo, like dropping 5 nears in a single turn to completely hijack the opponent's laser grid.
Yeah, and that is a core strategic tension in GoLuminamics.
The slow burn versus the big explosive turn.
Exactly. You can trickle out pieces turn by turn to slowly build your network, or you can stockpile energy to orchestrate these massive, sudden tactical shifts.
Are there any other modes? What if I just want to build lasers without the math homework?
Well, the repository does mention an infinite energy mode.
Oh, nice.
Yeah, it's for players who want a pure, chaotic sandbox experience. But the standard mode forces you to budget.
Makes sense. But simply placing the stones on the board is only half the mechanical equation, isn't it?
Right. The true depth lies in how you orient them.
And this is where the mechanics depart from almost every traditional grid-based game I've ever seen.
Yeah, this is the kicker.
Players can right-click to rotate their stones, and they aren't restricted to just 90-degree increments.
Not at all.
The system allows you to rotate a mirror or splitter anywhere from 0 to 360 degrees.
To any angle you want.
But wait, on a rigid square grid, an 11-degree or a 47-degree angle means the laser beam isn't going to snap neatly to the grid lines.
Nope, it ignores the grid lines.
It's going to travel completely off-axis, grazing intersections diagonally. My initial thought is that calculating those trajectories visually would be near impossible for a human player.
It would be impossible, utterly impossible without the underlying technology running the board.
So how does the game handle it?
Well, GoLuminamics doesn't just draw abstract lines. It runs on a real-time laser physics engine built entirely in Python.
Okay, so it's doing actual physics simulation.
Exactly. Specifically, it uses a framework called PySide 6.
I've heard of that.
Yeah, for those unfamiliar, PySide 6 is a set of Python bindings for the Qt toolkit. It's heavily used for developing complex, scalable graphical user interfaces.
Right, so this framework allows the game to render those continuous floating point trajectories flawlessly over the discrete grid.
Yes. The engine is actively doing the heavy mathematical lifting.
It's calculating the exact raycast of that off-axis beam.
It continuously calculates the ray path. And this shifts the player's cognitive load from just spatial blocking to dynamic, real-time geometric planning.
Because you aren't doing the math in your head, you're just aiming.
Right. If you angle a mirror at 17 degrees, the engine computes exactly where that beam will travel across a 39 by 39 expanse.
And remember the rule for territory. Any intersection the light touches is yours.
Exactly. So players are effectively sweeping their beams like a spotlight.
Making micro adjustments to graze as many grid intersections as mathematically possible.
Yes. You are literally tuning your pieces like you're calibrating a telescope.
Adjusting the rotation down to the single degree, aiming for maximum coverage.
And the payoff for all this calculation is the firing phase.
Right, because the lasers aren't always on, are they?
No, they aren't. The documentation mentions you hit the space bar to actually activate the network.
Oh, that must be satisfying.
It's the moment of truth. You hit space, the lasers enter from the board edges, and that's when you see if your optical circuit actually works.
It validates all that geometric planning. But wait, if the laser defines the territory and the board is populated by both players' pieces, these beams are inevitably going to cross paths, right?
Oh, constantly.
Or they're going to strike enemy components. I'd assume hitting an opponent's stone disrupts their circuit? Do you capture the piece, or does it just block your beam?
You capture it outright.
Really?
Yeah. If your laser beam hits an opponent's stone, that piece is removed from the board entirely. And you score an immediate +2 points per captured stone.
Wait, so the capture mechanics are instantaneous. You essentially snipe a piece with a laser from across the board.
You do. It's brutal.
That completely upends traditional Go strategy.
Yeah.
In normal Go, capturing a stone requires painstakingly surrounding it on all four sides over multiple turns.
Right, it takes a lot of setup.
But here, you're weaponizing the light itself.
You're weaponizing the light, but remember, the opponent has the exact same capability.
Oh, right. Mutually assured laser destruction.
Exactly. Every piece you place on the board serves as both a tool for your network and a potential vulnerability.
Because it can be shot.
Right. If you place a mirror to expand your territory, you might inadvertently expose its flank to an incoming enemy laser.
Ah, I see.
This creates incredible tension. Players have to decide whether to build a safe, enclosed internal circuit to maximize their own territory or aggressively angle their mirrors outward to shoot into the opponent's territory and dismantle their infrastructure.
So it's offense and defense happening simultaneously.
Completely intertwined.
A block could easily become a liability if the opponent adjusts the splitter by just 2 degrees.
Just a slight nudge and your piece is gone.
Human minds grappling with a 39 by 39 grid, managing an energy economy, adjusting continuous angles, and dodging laser snipers. I mean, that sounds like an immense cognitive load.
It is a lot to process.
The sheer computational power required to calculate sub-degree raycasts over a vast board is exactly why the developers built an environment not just for humans, but for algorithms.
Yes, and this is where it gets really sci-fi.
The repository includes a feature called the AI Arena.
Which is, the AI Arena elevates the project from just a clever game to a fascinating computer science experiment.
How does it work?
This mode allows large language model agents, LLMs, to battle each other directly on the grid.
Okay, this is where we need to dig into the mechanics of artificial intelligence. Because an LLM is fundamentally a text predictor.
Right. It's just predicting the next word.
It processes tokens of text, predicts patterns, and generates the most statistically likely subsequent text. But we just established how difficult it is to visualize a 360-degree floating point angle on a discrete grid.
It's hard for us, let alone a text bot.
Exactly. How can an LLM, a text-based engine, truly understand spatial reasoning, off-axis geometry, and optical physics?
Well, translating a visual geometric environment into a format an LLM can parse is a massive technical hurdle.
Because the AI doesn't have eyes.
Right, it doesn't see the glowing neon lasers like we do.
So what does it see?
Instead, the board state has to be meticulously tokenized. The game engine likely translates the entire 39 by 39 grid into a complex, structured text format.
Like a JSON object or something.
Yeah, exactly, or a coordinate matrix. The LLM receives a prompt that essentially says, opponent mirror located at coordinate 1214, rotated at 45.3 degrees, incoming laser threat vector approaching from coordinate 12.0.
The prompt engineering required for that must be staggering.
It is intensely complicated.
The AI has to read that string of text, mathematically conceptualize a laser traveling across the grid, reference its internal strategy playbooks, and then output a text command to counter it.
Yep.
It has to generate a response like, place splitter at coordinate 12, 10, rotate 135 degrees, cost 1 energy.
Exactly. The AI must evaluate the tokenized board state, manage its energy reserves, and determine the optimal placement and rotation of a piece, all to either defend its infrastructure or expand its territory.
That is mind-blowing.
Watching algorithms attempt to master a game with minimal randomness but infinite geometric possibilities, it provides incredible insight into how machines process complex, multi-layered resource management tasks.
It really highlights the difference between discrete and continuous variables in AI training, too.
Oh, absolutely.
Like if you look at chess, there's a massive number of possible moves, but the state space is discrete.
Right. A knight moves in a very specific, unchanging L shape.
Yeah. The AI just has to search a tree of finite possibilities. Even in traditional Go, where the board is larger and the move tree is exponentially bigger, the stones still snap to specific grid points.
And they never move once placed.
Right. But GoLuminamics introduces continuous variables.
Yeah, the 360-degree rotation means the state space, the total number of possible board configurations, isn't just exponentially larger, it basically borders on infinite.
Because a shift of a single degree on a mirror completely changes the trajectory of the laser.
Which in turn changes which intersections are illuminated.
Which changes the territory score.
It's cascades.
It's like asking an AI to play a game of billiards, but every time the cue ball hits a bumper, it splits into 2 cue balls, the table keeps getting bigger, and the AI has to calculate the exact angular momentum of every resulting collision, purely by reading a text transcript of the table.
That is a terrifying but accurate analogy.
It's absurd.
But by letting LLM agents battle each other in this AI arena, the developers are actively pushing the boundaries of what text-based models can comprehend about spatial and continuous physical environments.
They are testing whether semantic understanding can successfully map onto geometric reality.
Yes. And the repository mentions that the AI arena includes real-time visualization.
Oh, so you can watch them play.
Yeah. You can sit back and observe how these models attempt to untangle the optical physics.
That sounds mesmerizing.
It is. You might see one model adopt a highly defensive strategy, building tight loops of light, while another model rapidly depletes its energy, dropping splitters to chaotic effect.
So it's a live-action view of machine learning attempting to parse physics.
Exactly.
Yeah.
And this directly ties into the overarching design philosophy of the project,
Which is?
emergent complexity. The creators designed GoLuminamics so that the core mechanics are incredibly simple. Spend energy, place a piece, rotate it, and fire a laser.
It takes minutes to learn.
Right. But because those simple rules govern continuous variables, the implications generate a depth that takes a lifetime to master.
But despite that massive depth, the documentation notes that matches are designed to be relatively fast, right?
Yeah, surprisingly fast.
Like a typical game wraps up in just 15 to 30 minutes.
Which is perfect.
That's a huge departure from traditional Go, where a serious match can take hours or even days.
Oh yeah, those can be marathons.
But here, you get an intense, highly concentrated strategic burn, and you're done in the time it takes to drink a cup of coffee.
You get the intellectual rigor without the marathon time commitment.
So why is the pacing so tight?
Well, the pacing is tight because the territory swings can be so dramatic. A game ends through one of a few built-in victory conditions.
Okay, what are they?
The most common is the time expires condition, where whoever has the highest score when the customizable timer runs out is declared the winner.
Okay, so managing the clock adds a whole new dimension of pressure.
Huge pressure.
You might see a brilliant, board-clearing 42-degree laser bounce. But if you don't have the time to calculate the exact rotation, you just have to settle for a safer, less optimal move.
Exactly. You have to think fast. There is also the mutual pass condition.
Which is similar to regular Go.
Right. If both players evaluate the board and determine that no further piece placements will net them a positive energy or territory return, they can both pass their turn.
And the game ends.
The game ends, the engine tallies the illuminated intersections, and the highest score wins.
Simple enough.
And players can also simply surrender if their network has been completely outmaneuvered.
A tactical withdrawal when you realize your opponent's splitters have completely boxed you out of the grid.
There's no shame in it.
But the repository highlights a specific, dominant way to win called total victory.
Oh, total victory is the ultimate flex.
How does that happen?
It occurs when one player achieves overwhelming optical dominance. If you reach a score difference greater than 50 points over your opponent, or if you manage to control more than 80% of the territory on the board.
80%. That's
Yeah.
almost the whole board.
If you hit those thresholds, the engine recognizes that a comeback is mathematically impossible and just calls the match early.
It's an automatic mercy rule.
Pretty much.
Though the documentation does point out you can disable this by turning on infinite score.
Oh yeah, if you want a grueling, play to the bitter end type of game where you hunt down every last enemy mirror.
Which honestly sounds kind of fun too.
It does.
When you look at the entire scope of this project, it really is a brilliant synthesis of concepts. You have a beautiful UI rendering neon laser visuals, smooth physics animations calculated in PySign 6, and complex AI integration.
And all of it is built out in the open.
That's the best part.
The project being open source is a vital detail. It is licensed under GPL v3.
So what does that mean for the community?
This means the underlying code isn't just visible, it's freely available for modification and distribution.
Anyone can just grab it.
Anyone can fork this repository, adjust the physics engine, introduce new types of optical stones, or train entirely new LLM architectures in the AI arena.
It is a collaborative space for developers blending old-world strategic philosophy with modern computational physics.
Exactly. It translates the heavy geographical weight of territory control into the literal speed of light.
Which brings us back to where we started. We talked about how traditional games mapped the architecture of human intuition.
Right.
In Go, you have to feel the shape of the board and anticipate spatial flow.
And in chess, you test computational foresight, visualizing discrete moves several turns in advance.
But GoLuminamics introduces a paradigm that requires both, happening simultaneously over continuous angles.
Players, whether human or artificial, are forced to think dynamically and reactively.
Because you are no longer navigating a static map.
No, you are navigating a shifting current of energy.
So if you take anything away from this deep dive, let it be this final thought to ponder.
Let's hear it.
If classic board games tested the limits of human intuition, and modern LLMs are now learning to navigate continuous, glowing optical networks in a virtual arena, what kind of intelligence, human or artificial, is ultimately best suited to master an environment where strategy isn't sitting quietly on a wooden board, but is literally moving, bending, and splitting at the speed of light?
I mean, the victor will be whoever can adapt their geometry the fastest on a battlefield that never stops shifting.
Well said. Until next time, keep exploring, keep questioning, and keep diving deep.